You have learned X-ray, you have learned CT scan. The next one you need to learn now is ultrasound. Okay, now what is ultrasound in the first place? Ultrasound is actually just sound waves. But the thing is that we tell you that specifically ultrasound is sound waves whose frequency is above 20 kilohertz. Okay, any sound wave that has frequency above 20 kilohertz is considered to be ultrasound. Any frequency of sound waves above 20 kilohertz is considered as ultrasound. This one is not audible to the human ear. You cannot hear ultrasound. Okay, above 20 kilohertz, the human ear cannot hear it. Okay, only bats will be able to hear it, or whales. Ultrasound is basically you using sound waves to produce a body image. All right. Now you are required to know how we produce ultrasound, just like we require you to know how we produce X-rays. Okay. Now how we produce ultrasound in the first place, this one I will need to refer back to something else from your last chapter. For the chapter of electronics that I've done with you guys some time back, you remember that for the chapter of electronics, the one with the op-amp, I actually skipped one small portion of your sensing devices. Remember your sensing devices? I mentioned to you, you have your LDR, your thermistor, your strain gauge, and then after that, you have something called a quartz crystal or piezoelectric transducer. Okay, now this one here is where I will have to explain it because medical imaging will need you to know this. All right, now to put it simply, wait now, there's another thing here just now. Just now I have something. Give me a second. Oh, I did not give you guys the drawing. Okay, can you guys just give me a second? I did not send to you guys the screenshot, I think. Oh wait, I did. It's just that I did not use it here. Give me a second. I need to find the diagram. Where is it? Okay, yeah. Just now I sent to your chat group. Wait, I don't think you guys can see this. Let me just change it to PDF first. Wait on, sorry about the delay. Quartz crystal. Okay, now I should have it. Okay, just now I sent to your chat group this little diagram here. Okay, you should have this little diagram here. You can see it from your chat group. So I'm going to explain based on that. Now, just like I told you, when you want to, you can use ultrasound to produce an image of your body structure. Part of the syllabus requires you to learn how is ultrasound produced in the first place. Now, what we'll just tell you now is this. If you want to produce ultrasound, a piezoelectric transducer is used. Okay, a piezoelectric transducer is used. Okay, you want to produce ultrasound, you use something which we call a piezoelectric transducer. Okay, Just like in X-ray, we tell you if you want to produce an X-ray, you need to use an X-ray tube. So for ultrasound, if you want to produce ultrasound, you need to use something called a piezoelectric transducer. Now, piezoelectric transducer, the example of piezoelectric transducer is quartz crystal. Okay. Piezoelectric transducer is a general name. The actual name of a piezoelectric transducer is quartz crystal. The terms are interchangeable. You say piezoelectric transducer, it means quartz crystal. If you say quartz crystal, it means piezoelectric transducer. They mean the same thing. Okay, so if you want to produce ultrasound, you need to use a quartz crystal. Now, quartz crystal is unique in one sense, or piezoelectric transducer is unique in one sense, in the way where we tell you that if you have sound waves, you can change it to EMF or PD. And then likewise, if you have EMF or PD, you can change it to sound wave. This is what makes piezoelectric transducer unique. Okay, when you have a piezoelectric transducer, you can change sound waves to EMF or PD, or if you have EMF or PD, you can change it to sound waves. Okay, so I will just go through how it does so for these two different conversions. Now, as I mentioned to you, a piezoelectric transducer, an example of that is your quartz crystal. Okay, now when you're talking about a quartz crystal, the molecular arrangement is silicon O4. And if you look closely how the molecular structure is, it will be the silicon ion in the center with the 4 oxygens bonded to it. In 3D, it actually looks like this. Okay, in 3D, the structure looks like this. The positively charged silicon ion and the negatively charged oxygen ion. Okay, so far so good. Now, then after that, before we go any further, I have to mention to you something about polarity and net charges. Now, when you're talking about polarity and charges, net charges, you could have some cases where you do not have net charge, but you have polarity, right? What do I mean by that is, if you look at the example here at the bottom here, if let's just say I have an object which has both positive and negative, but the positive and negative are at exactly the same spot, I would say that this thing has no net charge. It also has no polarity. But if, say, for some odd reason, I do something to the material such that the positive go towards this end and the negative go towards this end, I will still say that there's no net charge, but there's no polarity in the object right now. Okay, if I do it the other way around right now, where the negative now go to this side and the positive still goes to this side, I will still say that this object has no net charge but has a polarity, just that the polarity is opposite to this one. Okay, so you can have something that has no net charge but has polarity. Now for quartz crystal, you're talking about something similar here. Your quartz crystal would have is, when your quartz crystal is unstressed, you don't compress it, you don't extend it, your centers of positive and negative charge are considered to coincide. Now, why is center of positive and negative charge? It's just simply the point where the whole charge is assumed to act. The concept is similar to center of gravity that you learn in AS. Center of gravity that you learn in AS was a point where you assume the weight of the object is acting. It's a point where you assume the whole weight of the object is acting. So you can also do the same thing for centers of charge too. The concept is the same. It's a point where you assume the whole charge is assumed to act. So for your case here, your quartz crystal actually has a positive and negative charge. Positive is because of the silicon, negative because of the oxygen. So here you assume that the centers of the positive and negative charge are coinciding when the quartz crystal is unstressed. Your quartz crystal has no net charge, no polarity now. But what happens when you go and compress your quartz crystal, or when you try to stretch your quartz crystal? When you compress or extend your quartz crystal, you are actually changing the structure a little. You imagine that if your quartz crystal looks like this, a tetrahedral structure like this, when you compress and extend it, this part here may stretch down a little, or this part here may go up a little, right? So as a result of that, what will happen is that when you stress your quartz crystal, either by compressing or extending it, your centers of positive and negative charge will no longer coincide. You now have polarity here. You have no net charge, but you have polarity. Okay, now it's this one here, this fact here, that will be used to explain how it converts sound waves to PD and PD to sound waves. Okay, so now let's just go through the part how it converts sound waves to PD or EMF first. Now, say for example, you have your quartz crystal. This one is your quartz crystal, the green color portion here right now. If it is unstressed, the centers of positive and negative charge is coinciding. Okay. Now, this quartz crystal right now, what I do is that I will coat the opposing faces of the quartz crystal with some sort of metal, some sort of electrode. Normally, we will coat it with, say, silver. Okay, argentum, silver. So once we have coated the quartz crystal with electrodes with metal at the opposing faces, we connect it to a voltmeter, say for example, or ammeter lah, if you would. Now, this is the crystal when it is unstressed. You have no polarity. But what happens when you compress it and extend it? Now, if you want to compress and extend your crystal, what you just need to do is that you need to expose the quartz crystal to sound waves. You remember sound waves are just pressure variations of the air, where the air is compressing and the air is expanding, right? So if you have sound waves that is incident on your quartz crystal right now, the air around your quartz crystal is continuously compressing and expanding. It's actually pressing onto your crystal, it's actually pulling on your crystal. It causes compression and extension of your crystal. Now, the compression and extension of your crystal will cause your quartz crystal here to have a polarity. So if originally they did not have any polarity, now it suddenly has polarity. So say for example, right now, your quartz crystal is in a state of compression. You now have a polarity of, say, positive here and negative here. Now, when this part here becomes negative, what we will tell you is that the negative here will repel an electron away from the electrode. The electron will now flow from here to here to here, back to here. So once the electron flows one full round here and reaches the other electron, it will be deposited at the other electron. Okay. Now, at this portion here, when your electrode lost one electron, it will cause the electrode to become positive because you lost one electron. Okay. But on the other electrode, when the electron gets deposited here, your electrode here has gained a negative electron, so it becomes negatively charged. Okay, but the important thing to know here is this: once you have polarity, you repel electron away, electron will move from here to here. You actually have current flow, okay, because you have flow of charges. Here you notice that your electron is flowing in this direction from bottom to up. Okay, just understand that one first. Now, what if your sound wave causes the compression, extension of your quartz crystal? So if it causes extension of your quartz crystal, your polarity will now change. Instead of being positive, negative here, now this one is negative, positive. So same thing will happen. If this one here is negative, it will cause an electron to be repelled away, and then you go the other side and come to this side. So when the electron is repelled away, this side loses one electron, it becomes positive. This side gains one electron, it becomes negative. But what is of interest to you is how the electron has flowed, the direction in which it has flowed. It went from here to here to here, right? So you see now your electron flow is here, going down. If before this, it was going up. Now it's going down. So you see now you have current flow in opposing directions when your compression and when you have compression and extension. Now, in this manner here, you see that if you have current, you're definitely going to have PD. You can only have current when you have potential difference, when you have voltages. So here it's correct to say that you have actually changed your sound waves to PD, to voltages. Okay, if your sound wave has this kind of variation, your voltage variations that you produce will be exactly the same frequency. Okay, they will be having same frequency. If this one was say 100 hertz, the voltage that you produce would also be at 100 hertz. You're changing your sound wave to voltage variations of the same frequency. Okay, this is how sound wave is producing your EMF or your PD. Okay, now the converse is also true. If you switch it around, if you have the same quartz crystal here like this, you connect it to a source of PD, a source of alternating PD, alternating voltage that looks like this. This is voltage versus time. You connect it to a source of alternating voltage. What will happen is that your quartz crystal will now produce sound waves instead. Okay. Now, when you're talking about alternating voltage, you would say that there are certain portions that are positive, certain portions that are negative, right? There'll be certain times where it's positive, negative one side and negative, positive the other side, right? So if you look at the example now, this is before you switch on the power supply. Once you switch on the power supply, it could be that your power supply, this is negative, this is positive. Then the other cycle will be this is positive, this is negative. If this is negative, this is positive. This being negative will cause the electrode here to be negative. This being positive will cause the electron here to be positive. When this is negative, this is positive, it causes your polarity to be like this. That would mean that your crystal is under compression. If you have positive and negative here, positive will give you positive here, negative will give you negative here, it will give you this polarity similar to this. So this one is equivalent to the crystal being extended. So if your alternating voltage is continuously changing polarity, you notice that your crystal is continuously compressing and extending. It's actually vibrating. It is compressing at one end, it's extending in one end. So when your crystal is compressing and extending continuously, is vibrating continuously, it will now produce sound waves. Okay, so in this way, you've actually caused PD to produce sound waves. This is one way in which you'll produce ultrasound. Okay, here we'll just say that an applied PD causes the crystal to distort. If you have negative positive here, it will become compressed. If you have positive negative here, it will cause the crystal to extend. If you have alternating PD means that the polarity keeps changing. That means your crystal will keep compressing and extending. It will now vibrate. So when it vibrates, it now produces sound wave of same frequency. Now, if you apply a PD of 20 kilohertz here, you're gonna produce sound waves of 20 kilohertz. Remember I told you ultrasound is actually any sound waves whose frequency is above 20 kilohertz. If your alternating PD has frequency of 20 kilohertz, the sound waves that you're going to produce is also going to be 20 kilohertz. You're already producing ultrasound now. Okay, so this is how you use PD to produce ultrasound. Okay, now explain the principles behind the generation of ultrasound waves for diagnosis in medicine. It is something like what I've just explained to you just now, but this time put in words. Okay, now this one, you could say that when you want to generate ultrasound waves, you need to have a quartz crystal that is coated with silver electrodes at opposite faces. When a PD is applied across the crystal at the electrodes, the centers of the positive and negative charge will shift and are no longer coincident. The crystal now changes shape. The part where it distorts, this is the part. You see, when just now I mentioned to you, you apply a PD here, your centers of positive and negative charge will no longer coincide. Okay, it will no longer coincide, your crystal will start to distort actually, so it's either compressed or extended. That is what this one means. Okay, the crystal changes shape. This is you applying a particular PD, but you apply an alternating PD or continuously changing PD, that will mean that your crystal will continuously change shape. In other words, it is vibrating. So when it vibrates, it will produce ultrasound. Okay. Then after that, here they say the natural frequency of crystal is in the ultrasound frequency range. The crystal is sized so that it vibrates in resonance. Okay, if you want to make it simple, this is actually the actual marking scheme answer lah. I mean, if you don't like the idea of the part where we talk about the coating receiver electrodes, the centers of positive and negative charge no longer coincident, that part, if you don't like that answer, I think you don't really need to bother so much about that, because this one is actually from the older marking scheme. Last time in the older years, when they asked you principle of generation of ultrasound waves, this point was inside. But nowadays, the newer ones, they don't really bother so much about that. You can actually get away with omitting that. If you don't want to talk about that, it will be this one. A quartz crystal will distort when you apply a PD across it. Applying alternating PD causes oscillations or vibrations. The natural frequency of the crystal is in the ultrasound range. When applied frequency is natural frequency, the crystal will start to resonate. Okay, there are two variations of the answer. This one is more like a more complete one, but this is the shortened version of it. So it's up to you which one you want. Okay, so I'll give you maybe a few minutes to copy this. Both answers if you want to, so you can make a comparison. Right. Okay, right. While you're copying, I just need to explain a bit about the last part here. Now you get the idea that you need to apply an alternating PD to cause the crystal to vibrate to produce ultrasound. But then why is it that suddenly we talk about natural frequency of crystal is in the ultrasound frequency range and that the crystal is sized so that it vibrates in resonance? It has something to do with this. If I just refer back to that little diagram that I showed you. Okay, just now I told you that whatever frequency you apply at the supply would also be the same frequency of the sound that you produce. That is correct. So the thing here would be this. If I had 20 kilohertz here, I will also have 20 kilohertz here, which would in turn mean that it is ultrasound. But the thing is that this ultrasound that I produce here, the amplitude may be small and it could also be big. If it is small amplitude, that means it is not really that good. You want to have a big amplitude of your ultrasound. Okay, let me just illustrate this. Say for example, you learn under your oscillations that there is something what we call driving frequency, something what we call natural frequency, right? Say for example, right now, the natural frequency of your crystal is say 10 kilohertz, but then the voltage supply that you apply is 20 kilohertz. Now, this one here could be thought of as your driving frequency. Then the natural frequency of your crystal could be thought of as 10 kilohertz here. Now, if you apply 20 kilohertz here, you will produce ultrasound waves of 20 kilohertz. All right. But the thing is that because your driving frequency here does not match your natural frequency, the waves of this frequency that you produce would be weak. The amplitude isn't that big. So if you want your amplitude of your ultrasound waves produced to be large, in other words, you want to have strong ultrasound waves, what you need to do is that you need to change the natural frequency of this crystal. Okay, so what you need to do is that you need to cut your crystal, or you need to size your crystal in such a way that its natural frequency is also 20 kilohertz, so that when you go and apply a voltage supply, that is at 20 kilohertz, what will tell you now is that your natural frequency and your driving frequency are now the same, so you have resonance. Your crystal now will vibrate at 20 kilohertz, but it will be vibrating with maximum amplitude. It will be vibrating with a very large amplitude. So you will produce ultrasound wave of 20 kilohertz, but is strong with large amplitude. Okay, that is more useful to you. You want to have strong ultrasound waves. You do not want to have weak ultrasound waves. Okay, so that's why here your answer made mention of things like natural frequency. Okay, they wanted your crystal to have a natural frequency in the ultrasound frequency range, meaning at the 20 kilohertz range, so that later on it will vibrate in resonance. Okay, this is the other point here. Right, so maybe I'll give you a minute or two to copy this. Right, so let me just clear off this one. Okay, right, so I think you should have been done with this already. At the very least, maybe you copied this already or this one already, but not to worry, you can just refer to Google Drive later for the complete answer. Okay, so let's move to page 25 of your worksheet. All right, if you look at page 25, now page 25 will be explain the main principles behind the use of ultrasound to obtain diagnostic information about internal body structures. Now, when you look at this question and the question before that, they might look similar, but they're talking about entirely different things. This one is talking about how you generate ultrasound waves for page 24. Page 25 is talking to you how you use ultrasound waves to obtain diagnostic information about internal body structures. In other words, it's asking you how do you produce an image of your body structure using ultrasound. Okay, now this is where we need to go to this part of your notes, page 13 of your notes for medical imaging. Right, now you covered the part of how we produce ultrasound waves. Now we need to cover the part of how are we going to use the ultrasound waves to produce an image. So take for example right now when we're talking about ultrasound. Now ultrasound has a very curious property in the sense that it is very easily reflected. Now if you remember how when we did x-rays earlier in the chapter, we said that if you want to produce an image of your body, you say this is your some portion of your leg with the bones inside here. If you want to produce an image of your leg, you will have to have a film here, an x-ray film here, and then you need to have an x-ray going through your body being scanned, right? Going through the body being scanned, right? Isn't it? If you want to produce an image using an x-ray, the idea was that you need to have an x-ray beam passing through the body being scanned. You actually want the x-ray to pass through your structure, to pass through the body being scanned, so that it can actually be incident on the film behind your body and darken the film, right? That is how your x-ray works. You need to have an x-ray beam passing through your body to darken the film behind. You actually want the x-ray to pass through your body, okay, in order to produce an image of your body structure. Now for CT scan also you had a similar concept. If you have something you want to scan, you have to cut it into slices, scan it in slices, and then when you want to scan it in slices, you have to scan in 4 different directions. But the same thing also would be said here. You actually need your x-rays to pass through your medium and be detected somewhere behind your medium itself, right? So here for CT scan and X-ray, you notice that the similarity between them is that you actually need the X-ray to pass through your medium. It must pass through the medium in order for you to get some sort of information for you to produce your image. Okay, that is what X-ray was. But for ultrasound, we don't necessarily want your ultrasound to pass through your medium, and then we don't really want to collect the ultrasound behind the body being scanned to produce an image. You see, in X-ray and CT scan, we need the X-ray to actually having passed through the body being scanned in order for us to produce the information about the image. Ultrasound is different. They don't rely on the ultrasound having passed through the object and then gone behind it in order for you to be able to make use of it to produce an image. Instead, what we rely on is the reflection of the ultrasound as it passes through the body. We make use of the reflection of the ultrasound to produce an image of the structure. Okay, we don't rely on it having passed through the medium and then making use of the ultrasound that actually is remaining after passing through the medium before we produce an image. We make use of the reflection as it passes through. Okay, so what we mean by that, I'll just explain here. Now, when you have ultrasound, say for example, right now, I give you a case where you have ultrasound passing through, and then the ultrasound is actually passing through two different mediums. You have, say, medium 1 and then medium 2. The line that you see here is what you call as the boundary between mediums. This is the boundary between two mediums. Okay, now if you have an ultrasound and it hits the boundary between two different mediums, what will happen is that that ultrasound will split up. A portion of it will be transmitted and then a portion of it will be reflected. So I mentioned that one curious property about ultrasound is that it is very easily reflected. Normally, it will be reflected when it hits the boundary between two mediums. Okay, medium 1, medium 2, the boundary. Once your ultrasound hits the medium, the boundary, it will split out. Part of it will be transmitted, part of it will be reflected. So say for example, right now I tell you that the intensity of the ultrasound here is originally I. So once it hits the boundary between the medium, it will split up. Part of it is reflected, part of it is transmitted. So you will say that intensity I is actually equals to the intensity reflected plus the intensity transmitted, because both of these came from the same intensity in the first place. Okay, this is the first relation that you need to know. Okay, now when it comes to producing an image of your body structure, we do not, as I mentioned to you earlier just now, we do not make use of the intensity that has actually passed through your medium to make an image. We make use of the reflected intensity to make an image. Okay, so we need to take the reflected intensity. We need to find a way to capture that reflected intensity and make use of it to produce an image of your body structure. Okay, so the thing here also is this. Although I said that we need to make use of the reflected intensity to make an image of the body structure, we don't actually need a lot of the intensity reflected. We only need a little of the reflected intensity. Okay, we do not need a lot of intensity reflected. We only need a little. Okay, here the first thing is that you need the reflected intensity to produce an image. That's correct. But for the intensity that is reflected, we also do not need a lot. We only need a little. Okay, you only need a little of the intensity reflected to produce an image of the body structure. So if you want to have very little intensity reflected, you want to, because you see, there's a problem if you say that you want to use a very large intensity reflected. If your ultrasound comes here and you have a very large intensity reflected, that will mean that you would have very little intensity transmitted. You will have very little intensity transmitted. Your ultrasound cannot go deep into your body structure or scan deeper into your body. Okay, but if on the other hand your intensity reflected is very low, that will mean that your intensity transmitted is very high. That means it can go much deeper into your body structure. What I mean by that is that I think I better illustrate it to you. Say for example, right now I have 4 different mediums. Okay, as illustration. Okay, 1, 2, 3, 1, 2, 3, 4. If I want to be able to scan all 4 of these mediums, you need to have an ultrasound incident on the medium. It could be that, okay, maybe this one is your initial intensity of your ultrasound. If your IR reflected, if your intensity reflected is small, if your IR is small, intensity reflected is small, that means your intensity transmitted is big. That means it can travel much deeper into your body structure. What I mean by that is that here it maybe reflects a little, but then there's still a lot, so it can go deeper, and then it reflects a little, it can go deeper still, and then it reflects a little, it can go deeper still again, it reflects a little, and then it can go deeper again before it reflects again. Okay, so you having large intensity transmitted allows your ultrasound to move much deeper, and along the way it allows you to give off a lot more reflection at different mediums. So what you do is that you make use of these reflections to produce an image of your body structure. But if on the other hand your intensity reflected is very large, if your intensity reflected is very large, that will mean that the intensity remaining that you can transmit is very low. Okay, let me just clear this off. If your intensity reflected is very large, that means the intensity that you can transmit is very low. So what that would have meant would be that you don't have enough that can go all the way in. So you would have reflection here. It probably still is able to pass through the first medium. But then after that, because your intensity reflected is very large, you have very little remaining. So it becomes too small. It cannot go into the third and fourth medium already. So it just stops here. So you are only able to scan as deep as this. Okay. So there is a reason why sometimes we want the transmitted intensity to be very large, so that it can actually keep on going deeper and deeper into your medium, so that it can keep on reflecting and you can make that to produce an image of your body structure. The reflection that you have here, we only need a little. We don't need a lot. Whether or not it's a lot, whether or not it's a little, it has no effect on the image or the body structure that we are scanning. We just need a little. Okay, so the gist is that for the intensity of wave that is reflected, we only need a little of it in order to produce an image of the body structure. Okay, we do not need a lot. And also at the same time, we also need the transmitted intensity to be very large, so that it can actually go deeper and deeper into our body structure to be able to scan deeper. Okay, now if we want to calculate out how much intensity has been reflected, we need to make use of a certain equation called the intensity reflection coefficient, sometimes given the symbol alpha. Now your intensity reflection coefficient is actually this one. Okay, IR over I is equals to Z2 minus Z1 square over Z2 plus Z1 square. Now IR here is your intensity reflected. I here is your initial incident intensity. Okay, now what is your Z? Your Z here is some other physical quantity called specific acoustic impedance. All right, specific acoustic impedance is just simply defined as the product of density and the speed of ultrasound in the density, in the medium. Okay, density of medium and the speed of ultrasound in the medium. Okay, now see here, don't mistake it as the speed of light. Previously, before this C was thought of as your speed of light, right? In your case here, you don't use speed of light here. The C here specifically refers to the speed of the ultrasound wave inside the medium. Ultrasound is sound wave. It is not EM radiation, so you cannot use 3 times 10 power 8. Okay, right? So that Z here is the Z here. This one is the specific acoustic impedance for a particular medium. In your case here is medium 2. This is specific acoustic impedance for medium 1. All right. Now this one here, this entire expression, specifically this one, it indicates the proportion of intensity reflected at the boundary. In other words, it tells you the fraction of intensity reflected at the boundary. Okay. IR over I is important because it tells you the fraction of intensity reflected at the boundary. Okay. So the thing here would be this. If I want to have very little intensity reflected, I want to have a small fraction of intensity reflected, what should be the relation between Z1 and Z2? Okay. Now, what's the relation between Z1 and Z2 so that the fraction of intensity reflected is small will be given by this. Okay. Just like I mentioned to you, when you want to produce an image of your body structure, you want the intensity reflected to be as small as possible. You just need a reflection. You do not need a lot of it. Okay. So how do you ensure that the intensity that is reflected is small? The fraction that is reflected is small. So you refer to this little part here. I try to put it out again. IR over I is Z2 minus Z1 square, Z2 plus Z1 square. All right. Now, if you if you want to talk about the fraction intensity reflected, it will actually depend on the magnitudes of your Z1 and Z2. Okay. When you're talking about Z1 and Z2, you can talk about the difference between them. Okay. What we'll say here is that if the difference between the specific acoustic impedances is very large, meaning to say one of them is very much larger than the other, that will mean that you will have a large proportion of intensity reflected, a large fraction of intensity reflected. Why? Because you see, if this is much larger than this, the difference between them here is going to be large, right? As a whole, you can see that this thing is going to be large. This will affect this one, which causes this to be large also. This as a whole will now then be large. So your fractional intensity reflected is very large. And then you will have very little intensity transmitted. Okay. If on the other hand, your specific acoustic impedance has very little difference between them, meaning to say that both of them are similar to each other, we will tell you that you will have very little intensity reflected. You will have a small fraction of intensity reflected, because you can again also see from here, if IR over I is equals to Z2 minus Z1 square, Z2 plus Z1 square, if the difference between them is very little, where this and this are almost similar, that would have meant that this one represents the difference. Z2 minus Z1 will give you the difference, right? If this and this are almost similar, that means the difference is going to be small, very small. If this is small, that means this one is small. Okay, if this one is small, that means the entire thing is small. So your fractional intensity reflected will be small. If your fractional intensity reflected is small, that means your fractional intensity transmitted will be large. Okay, so this one is important to know because they will often ask you, how should be the magnitudes of Z1 and Z2 be if you want to have very little reflection or if you want to have very large reflection. The key thing is to look at the difference between them. If the difference is very large because one is very much larger than the other, this one will be large, this will be large, this will be large. If the difference between them is very small because they are very similar to each other, that means this will be small, this will be small, and this the entire thing will be small. Okay? So that is how you look at it. Now, if you wanted to find out the fraction of intensity transmitted, you can actually make use of what you have seen from the top, the one here. IR over I is equals to this expression, right? This one represents to you fraction of intensity reflected. The fraction of intensity transmitted, IT over I, would be equals to 1 minus IR over I. How do I know this? How do I get this expression? Remember just now at the beginning, at the top here, we mentioned this. Your incident intensity, once it hits the boundary, it will be split into two things, the reflected and transmitted intensity. So here, I will be equals to IT plus IR. I rearrange this one, IT will be I minus IR. Now, if I were to just divide by I for both sides of the equation, I'll get IT over I over I will give me 1, IR over I will give me this. So I get this, which basically just tells me that fraction of intensity transmitted is equals to 1 minus fraction of intensity reflected. Okay, this was obtained from this. Okay, so far so good with this. Okay, so this one is fine. Then I move on to the other part. Now that you know that the differences between the specific acoustic impedance will actually affect the intensity reflected, then you will be sometimes asked to explain why is it that in certain case we use certain things. Now, say for example, if you want to scan your human body, I say for example, in your case, maybe you have soft tissue here. This is your soft tissue of your body. You want to scan whatever is inside. This is basically air. All right. Now, say you want to use ultrasound to scan inside your body right now, which consists of soft tissue. This one here being your piezoelectric transducer. This one is the one that generates your ultrasound. Okay, it generates your ultrasound. This generates ultrasound for you. So now you know you have ultrasound coming out of your piezoelectric transducer. Okay, maybe I use this one. Your ultrasound coming out of your piezoelectric transducer. Okay, your ultrasound coming out of your piezoelectric transducer. You want to scan what is inside your body. Okay, now if you put your piezoelectric transducer or your ultrasound transducer directly onto your skin like this, which contains your soft tissue. So this one is your skin now. All right, this is your skin. Then beneath your skin is your soft tissue. If you put your ultrasound transducer directly onto your skin to scan whatever is inside your soft tissue, what will tell you is that it won't really be effective, because what we'll say here is that once you put your piezoelectric transducer onto your skin, there's actually going to be a layer of air in between. There'll be a layer of air. Your ultrasound transducer producing your ultrasound once it hits here, you will actually have two different mediums here. One of it is air, one of it is soft tissue. So your boundary is basically your skin here. All right. Maybe I need to use a different color. Your boundary is your skin here. Okay. Right. Where one side is air, one side is soft tissue. The thing you're interested in knowing is what is the fraction of intensity reflected? Is it going to be a lot or is it going to be a little? So if you look at this table, the specific acoustic impedance of air is 430. the specific acoustic impedance of soft tissue is 1.63 times 10 power 6. You see this is very different, right? Meaning the Z2 is very much larger than Z1. So from the previous page, you know that if Z1 and Z2 are very different, if difference between Z1 and Z2 are very large, you would know that IR would be very large because IR over I is equals to Z2 minus Z1. Wait, let me just redo this. Because in your case here, IR over I is equals to Z2 minus Z1 squared. Z2 plus Z1 squared. So the difference is very large. This one is large. This one will be large. So the entire thing is large. Okay. So your fractional intensity or reflected intensity is very large. So again, then if your fraction of intensity reflected is very large, it is not something that you want because your transmitted intensity will be very little. It won't be able to penetrate deep into your body. So you do not want that. Okay. So if you want to overcome this kind of problem, what do you have to do then? We will tell you that when you want to use your ultrasound transducer or piezoelectric transducer onto your skin, we will ask you to put some sort of gel. You say this is your same ultrasound transducer, and then this is your same thing here, which has soft tissue, and then you have air, and then this part here being your skin again. You still have ultrasound here. Now, if you want to have very little intensity reflected here, what we will tell you now is that you need to put some sort of gel in between the transducer and your skin. Meaning to say here, you put some sort of gel, water-based gel. Okay, water-based gel. You need to put something called water-based gel here, right? So when you put a water-based gel between your transducer and your soft tissue, there's no air in between because this one is something like liquid. It will fill up any gaps, so there won't be any air in between here. So you basically eliminated the layer of air here. So in that sense here, when your ultrasound travels, the medium that you're considering is only between the water-based gel and the soft tissue. This one will be your two mediums here. So now you consider water-based gel and soft tissue. What is the specific acoustic impedance? You look at what is the specific acoustic impedance of water and soft tissue. Water would be 1.5 times 10 power 6. Soft tissue would be 1.63 times 10 power 6. You see this one is very similar. Okay, so from the previous part of your notes, if the difference between Z1 and Z2 is very little, you will have very little reflection. Because if you look back at the equation, IR over I being Z2 minus Z1 squared over Z2 plus Z1 squared, if the difference is very small, because they're both very similar, this one will be small. Okay, that will in turn cause this one to be small, and in return it will cause this entire expression to be small. So fractional intensity reflected is very small. Okay, so you will have a very large intensity transmitted, so your ultrasound can travel very deep into your body and keep on scanning and keep on giving you information about your body structure, which is what you want. Okay, so this is one particular application of that, which the question will ask you. All right. Okay, so this part is done. Then after that, I need to talk a bit about yeah, absorption of your ultrasound through a medium. Okay, now absorption of ultrasound through your medium, this one isn't talking about your ultrasound that is reflected. This is talking about ultrasound that has actually traveled through a particular medium thickness. Now, this one would have some similarity with your X-ray. Do you remember that in your X-ray previously, I talked about this concept? If you had, say, this is for X-ray lah, right? If you have X-ray of initial intensity I naught, it passes through a medium with it passes through a medium with linear attenuation coefficient mu, and it has a thickness of X. Once this in X-ray with a certain intensity passes through the medium, its intensity will drop. Okay, its intensity will drop because your X-ray is being absorbed by your medium. Its intensity will drop in this manner, like this, an exponential decay curve. So that after you pass through that medium thickness, whatever comes out of the medium, the intensity here will no longer be the same as the intensity here. It will actually be lesser than the ones here. So if you're interested in finding out what is the remaining intensity here after the X-ray has been absorbed by the medium, I told you that you generally have an equation called I naught exponential negative mu x that you can use to find out what is the remaining intensity. So same concept here. You can apply it for ultrasound also. For ultrasound, if you have a particular medium of thickness x and the absorption coefficient k, which is this one, okay, your medium here is medium has thickness x and absorption coefficient k. If you have ultrasound with initial intensity I naught, as it passes through your medium, it will be absorbed by the medium, so that whatever ultrasound you get at the end here will not be the same as this one here. It will actually be less than the ones here. Okay, how the intensity of the ultrasound decreases with distance would be same like this one. Okay, so because it decreases in this similar manner, the equation that you use will also be similar. So in your case here, the equation you use would be this: I is equals to I naught exponential negative mu negative kx. The only thing that seems to be different here is k, whereas for X-ray it was mu. They're basically the same thing lah, actually. So if you do it as mu, you do it as k, it doesn't really matter. We don't really bother about that. But just know that the general form of the equation is the same. Okay, right? So the part where you talk about the ultrasound intensity decreasing as a result of it being absorbed by the medium is what we call as attenuation. Attenuation is decrease in intensity of the wave as it passes through the medium. The reason why there is a decrease in intensity is because it is absorbed by the medium as it passes through. So its intensity will decrease with distance. Okay, so that part is okay. This is for ultrasound. So we just go and do some questions first to internalize whatever we learned here. Okay, if you were to just look at page 25, we just now stopped at page 25, didn't we? So just have a look at page 25. Okay, have a look at page 25. This is March 2018 P42. Question 5. Alright, so explain main principles behind the use of ultrasound to obtain diagnostic information about internal body structures. Now, how is it that we actually use ultrasound to produce information about your body structure? First, we will say that pulses of ultrasound are reflected at the boundaries between media. The reflected pulses are detected by the ultrasound generator. The reflected signal is processed and displayed. The time delay between transmission and receive gives information about depth of boundary. The intensity of reflected pulse gives information about nature of boundary. You use a gel at skin to minimize reflection and maximize reflection at the skin. The degree of reflection depends upon the impedances of two media at the boundary. So this is the answer for use of ultrasound. If you want to make use of a diagram to understand it better, I will just draw it here. You can copy this in the meantime. Right, so I have the four mediums, 2, 3, medium 1, medium 2, medium 3, medium 4. This is my ultrasound. Okay, this is my ultrasound generator or transducer. This one produces my ultrasound. It's this. And this one would be this one is the sorry. This one is the pulse. This one is the pulse. This one is the time delay. This one is the refracted density. Okay, right. So now that I've done the diagram, maybe I just re-explain back the little point that you are copying with respect to the diagram. Okay, now you understood the fact that when you send ultrasound into your body, it will be reflected at the boundaries between the media. Okay, and your reflected pulse is what you want to take or what you want to detect, which would then be processed to give you an image of your body structure. So the idea was that if you have a certain medium, certain body with 4 different mediums, you want your ultrasound to keep going in, and at the same time, every single time it wants to go into a new medium or hits the boundary between two media, it will reflect. So the reflection, which is this one, is what you want to use to produce the image. Okay, it is this one here where we tell you that the reflection is used to produce image. Okay, that part is okay. Now when you send your ultrasound, there's another thing here that you need to know. We do not send your ultrasound continuously in. We send it in pulses, meaning to say a short burst of ultrasound, something like this. This is what we call as a pulse. You do not send it continuously like this. All right, we don't send ultrasound into the body continuously like this. Instead, we send it in a pulse. Okay, so the reason for us sending it in a pulse is so that we can detect the reflected pulse. Right, sorry, I did a mistake here. This is not emitted pulse. This is the emitted pulse. This is the reflected pulse. This is the emitted pulse. This is the reflected pulse. Okay, we normally, when we transmit your ultrasound, we do not send it inside with a continuous value. We don't send it continuously inside. we send it in pulses, right? The reason why we send it in pulses later on you will learn is because so that we can see the reflected pulse. Okay, now the reflected pulse is what we use to produce an image of your body structure. Specifically, what is it about your reflected pulse that we use? We make use of the time delay between the emitted and reflected pulse to tell us information about the depth of the boundary. Okay, if your boundary, if your medium or depth of your boundary is larger, that means your wave, your ultrasound wave will take a longer time to get back, right? So your time delay will be longer, right? The longer your time delay, that means the boundary is much deeper. Your medium is thicker, all right? Hence, that's why we say this. The time delay between the transmission and receipt gives information about the depth of the boundary. Your reflected pulse will take time to come back to your ultrasound transducer. All right, the longer the time delay it takes, that means the thicker the boundary. Sorry, the thicker the medium, the deeper the boundary. Okay, and then after that, the reflected pulse that you get at the end, the reflected intensity actually will tell you the nature of the boundary that it has hit. For example, if you say your ultrasound is traveling and it hits the boundary between two medium, the medium after that say maybe is one of it is say soft tissue, one of it say is bone. You do not expect the reflections of the bone and muscle to be exactly the same, right? Because the bone is a different material than muscle, right? So if your ultrasound hits bone and gets reflected, and your ultrasound hits muscle and it gets reflected, you do not expect the intensity reflected to be the same. The intensity reflected will actually be different. So in this sense here, we will actually say that the intensity of your of your reflected pulse will actually give you information about the nature of the boundary. It will give you an idea of what is it that you have hit. Is it bone? Is it muscle? Is it fat? Is it soft tissue? Okay. So these two about your reflected pulse is what gives you information about your image. They will tell you how deep it is and what is it that you actually hit. What kind of medium is it? All right. So this one here is something that I just explained to you. Why is it that you need to use a water-based gel to minimize reflection at the skin? And then this one here I also explained to you. Your degree of reflection depends upon the impedances of the two media. This is referring to your specific acoustic impedance Z1 and Z2. I explained to you that the differences between them will actually determine how much is reflected. Okay, so this one is only worth 6 points. You can choose any one of these three. What I've written here is actually the complete answer. All right, the common one I will normally write is this one, the time delay and intensity of reflected pulse. Okay, normally I write this, time delay and reflected pulse. If you write this one itself, this one is already the full answer. Okay, I would say that the last two here is something like really additional information. Okay, so far so good. Okay, so if this one is okay, then I move a little downwards before I give you guys a short break. Now, define what is specific acoustic impedance. Specific acoustic impedance is, as I mentioned to you, that little property called Z. Z equals to rho C. So specific acoustic impedance is just simply the product of density of the medium and the speed of sound in the medium. That's all. Okay. So that part is okay. Right. It's the product of the density of the medium as well as the speed of the medium in the speed of sound in the medium. Sorry. All right. Okay, then after that we go to the last one. Okay, the last one here is talking to you about two media have specific acoustic impedances Z1 and Z2. The magnitude of the specific acoustic impedance may be almost equal or very different. Okay, maybe almost equal or very different. State how the differences will affect the intensity reflection coefficient at the boundary between the two media. How would the magnitudes of this acoustic impedance being almost equal or very different affect this intensity reflection coefficient? This one is talking to you about this one, isn't it? Intensity reflection coefficient, as I mentioned to you, is this one, IR over I. Sorry, there is some problem here. This one is IR over I naught. My mistake. Okay. Intensity reflection coefficient is IR over I naught. Just now in your notes is I lah, but here I would just say I naught lah. The initial intensity is given by this. So as I mentioned to you just now, if your specific acoustic impedance is almost equal, that means the difference between them is very small. Maybe I need to write here. If the Z1 and Z2 are almost equal to each other, meaning the Z2 is almost equal to Z1, the difference between them will be very small. The reflected intensity will be small. So the entire term will be small. You will have small proportion of reflected intensity, large proportion of transmitted intensity. Okay. If on the other hand, your Z1 is very different from Z2, meaning to say Z2 could be very much larger than Z1, what will happen is that the difference between them is very big. This IR will be very big. The entire expression will be very big. So your fractional intensity reflected is very large. You will have very small fractional intensity transmitted. So here, if Z1 is almost equals to Z2, you will have small proportion of reflected intensity. Your coefficient is actually very small. If Z1 is very much larger than Z2 or Z1 is very much smaller than Z2, which is this situation here, you would have very large intensity reflection. You will have very large intensity reflected. So your coefficient is nearly equal to 1. The next question I'll go through is on page 27. Now for this one here that I wrote, if you copy this and you want to have a better understanding of what the little symbols mean, I would say this one is the better representation. The diagram here is a good representation. Okay, so this one here is your boundary between two medium. All right. If you have initial intensity, that initial intensity upon hitting the boundary between the medium, part of it will be reflected, part of it will be transmitted. The intensity reflection coefficient is talking about the ratio or the fraction of intensity reflected, which is IR over I naught. Okay. In your notes just now, the initial intensity is just I lah. Okay. Here I wrote it as I naught now. Just be careful about what the I, just be careful about your symbols. Sometimes it can be talking about different things, but they actually, sometimes the symbols may be different, but they mean the same thing. Okay, so this one is this. So if nothing else, have a look at page 27. Page 27 of your worksheet. This one should be something else. This one is June 18, P41. Question 4. I believe that question is repeated. Question 4, page 27 or question 4. Right. Okay. Page 27, question 4, which is this one. This one I think is very simple. Okay. There's nothing here to really talk about. They tell you piezoelectric transducer are used for generation of ultrasonic waves, ultrasound waves. State another use apart from ultrasound or piezoelectric transducer. You can say it's used in microphone. Okay. Now, just now I explained to you that your piezoelectric transducer can be used for two different things. Either you want to convert PD or voltage to sound waves, or either you want to convert sound waves to PD or EMF. So the part where you convert sound waves to EMF or PD is actually your microphone. You use it for microphone. So what happens in a microphone was simply something like this. Let me just draw a simple diagram to illustrate to you. You know, yeah. In a microphone, what you have been doing would be this. You speak into a mic, and then after that you have a speaker, right? This is your speaker, and then this is your microphone. Now inside your microphone, you would actually have a piezoelectric transducer or your quartz crystal. It will convert sound to voltage. Alright, so whatever sound waves that you have when you speak into the microphone will be converted into voltage variations. So once you convert your sound waves into voltage variations, it will be diverted towards the speaker. Your speaker will make use of your voltage variations and reproduce back your sound waves by causing the diaphragm inside your speaker to vibrate, and then you produce back sound waves. Okay, so in your case here, another use of piezoelectric transducer apart from producing ultrasound is in your microphone. Your microphone contains your piezoelectric transducer. Your sound waves from your voice will be converted to voltage signals or voltage variations. You direct it to your speaker will make use of your voltage variations to reproduce back your sound waves. Okay. Other choices of answer would be weighing scales, pressure sensors, lighters, spark generation, watches, clocks, regulation of time. Those could be one of the few uses of piezoelectric transducer. Okay. But the most common one is microphone. Whatever you have here is actually just a marking scheme answer. All right. So you can copy that. Okay, for part B, explain the main principles behind the use of ultrasound to obtain diagnostic information about internal body structures. Now, the part where they ask you to use, how do you use ultrasound to produce diagnostic information about internal body structures? We've actually done that same question in page 25. It's exactly that same question, exactly the same answer. So you can recopy it back later when you are free. So this one, I won't really bother so much about this.